Hello, dear students. Glad to meet you again in this session. In this session 2.11, we are going to discuss about filling of orbitals from chapter 2, structure of atom in grade 11. Before getting into today's concept, let us recall all the topics that we have discussed in the previous sessions.
In session 2.1, we have discussed subatomic particles and its classification. In session 2.2, we have discussed the atomic model, that is J.J. Thomson atomic model, Rutherford atomic model and its drawbacks. In session 2.3, we have discussed the dual nature of electromagnetic radiation. In session 2.4, we have seen the continuous spectrum, emission spectrum, absorption spectrum, atomic spectrum, and line spectrum of hydrogen. In session 2.5, we have discussed the postulates and explanation of Bohr's atomic model for hydrogen atom, line spectrum of hydrogen atom, and limitations of Bohr's model. In session 2.6, we have discussed the two developments, that is de Broglie's relationship and Heisenberg's uncertainty principle that leads towards quantum mechanical model of atom. In session 2.7, we have discussed quantum mechanical model of an atom. In that, we have discussed Schrödinger wave equation, significance of psi, the wave function. In session 2.8, we have discussed orbital and quantum numbers. We have discussed four quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and electron spin quantum number. In session 2.9, we have discussed the shapes of s orbitals, p orbitals, d orbitals, and f orbitals.
In session 2.10, we have discussed energy of orbitals, that is increasing order of energy levels of electron in an atomic orbital using n plus L rule. In that, we have discussed energy level diagram of single electron atom and energy level diagram of multi-electron atom. Learning outcomes. Students, at the end of this session, you will be able to list the rules of filling of orbitals in an atom and explain Aufbau principle, state Pauli's exclusion principle, and explain Hund's rules of maximum multiplicity. In the previous session, we have discussed the order of energy in orbitals using n plus L rule, right? In that, we have discussed a subshell with lower value of n plus L has the lower energy. And if two subshells have equal value of n plus L, then the subshell with lower value of n has lower energy. And we have learned that according to n plus L rule, the increasing order of energies of various orbitals is in the following order. Filling of orbitals. The filling of electrons into the orbital of different atom into the ground state is determined by the following rules. Only if it is the ground state, then it is determined by the following rules. They are Aufbau principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. Let us see all these rules one by one in detail. Aufbau principle. The German word Aufbau means building up. Building up of orbital means filling up of orbital with electrons. This Aufbau principle states that in the ground state of the atoms, the orbital are filled in order of their increasing energy. That is, the electron first occupy the lowest energy orbitals available to them, and then the electron enters the next higher energy orbitals. This increasing order of energies of various orbitals may be remembered by using diagonal rule of electron filling order. Diagonal rule begins with the top right corner. When you consider this box, this is diagonal rule of electron filling order. It begins with the top right corner and moves diagonally towards the bottom left corner, right? So already we know that the increasing order of energies of various orbital using n plus L rule is 1s less than 2s less than 2p less than 3s less than 3p. Goes on like this, right? We will apply this diagonal rule and check this order now. So it begins with the top right corner, means in the first diagonal line, it is 1s, right? So 1s we have written here. Then coming to the second diagonal line, we have 2s. It has to move from the top right corner towards the bottom left corner. Okay, so 1s, then coming to the next line 2s, then coming to the next diagonal line 2p, which is less than 3s, then coming to the next diagonal line 3p, 4s. You check with this n plus L rule also. Then after 4s, we have to coming to the next diagonal line. We have 3d, 4p and 5s, right? That's what we have written, 3p, 4d and 5s. So after 5s, now where we have to start? Again, we have to start from the top right corner. Okay, so we have 4D moves diagonally towards the bottom left corner. We have 5P, then 6S, right? So we have here 4D, 5P, 6S. After 6S, again we have to move to the top right corner. Next diagonal line, we have 4F, then 5D, then 6P and 7S, right? That's what we have written, 4F, 5D, 6P, 7F, and it will go on like this. So this diagonal rule of electron filling order is in accordance with the N plus L rule. So we can easily memorize this increasing order of energies of various orbitals using this diagonal rule of electron filling order.
Pauli's exclusion principle. This exclusion principle was given by the Australian scientist, actually he is a physicist, Wolfgang Pauli. According to Pauli's exclusion principle, no two electrons in an atom can have the same set of all the four quantum numbers. And his principle also stated that only two electrons may exist in the same suborbital, and these electrons must have opposite spin. Let us discuss this principle and its statement one by one in detail. According to exclusion principle, no two electrons in an atom can have the same set of all the four quantum numbers. Already we have studied about the quantum numbers. What are they? They are principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number, right? This principal quantum number determines the size and the large extent the energy of the orbital. From the value of n, we come to know that whether the electron is in the K shell or L shell or M shell and so on, right? So it determines the size of the orbital. Next, azimuthal quantum number. This azimuthal quantum number defines the shape of the orbital. That is, if it is an s orbital, then it is spherical in shape. If the value of L is equal to 1, we know that that is a p orbital and its shape is dumbbell shape, right? So this azimuthal quantum number defines the shape of the orbital. The third one is the magnetic quantum number. This magnetic quantum number m gives the information about the special orientation, that is whether it is in the x direction or y direction or z direction. So it gives the information about the special orientation of the orbital with respect to the standard set of coordinate axes. What are all the standard set of coordinate axes? That is nothing but whether it is in the x direction or y direction or z direction. And the last one is the spin quantum number m suffix s. This refers the spin of the electron, that is whether the electron is spinning in the clockwise direction or anti-clockwise direction. So, according to this exclusion principle, no two electrons. So, even though these two electrons present in the same suborbital, it doesn't have the same set of all four quantum numbers. That is why they have given no two electrons. So, no two electrons in an atom can have the same set of all the four quantum numbers. If you look at the values of these two electrons which present in the same suborbital, if you look at the values of n, l, m and m suffix s for these two electrons, it won't be same. At least one value of these quantum numbers differ from the other. For better understanding, let us take an example to understand this concept clearly. Let us take helium atom as an example and find out the values of all the 4 quantum numbers. The atomic number of helium atom is 2, which means it has 2 electrons, right? So let us find out the values of 4 quantum numbers for these 2 electron, first electron and the second electron. Since these 2 electrons present in the K shell, that is in the first shell, the value of n equal to 1. So the value of n for these 2 electron, first electron is 1 and second electron is 1. Coming to azimuthal quantum number L. The azimuthal quantum number L value ranges from 0 to n minus 1. In our case, what is the value of n? N equal to 1. So 1 minus 1, 0. So the value of L equal to 0, which represents suborbital S, which is spherical in shape. So the value of L for the first electron and the second electron, which is in the K shell, is 0. Next, coming to the magnetic quantum number M. The magnetic quantum number N value ranges from minus L to plus L through 0, right? So here the value of L equal to 0. There is no minus 0 or plus 0. So what is the value of M? The value of M is 0 for the first electron and as well as for the second electron. So the value of M for the first electron is 0 and the value of M for the second electron is also 0. Now coming to the 4th quantum number, that is the spin quantum number, which refers the spin of the electrons. We know it has 2 values, that is plus half and minus half. So the electron which spins downward direction, that is in the clockwise direction, will have the value plus half, and the next electron which spins in the upward direction, that is called the anti-clockwise direction, will have the value ms is equal to minus half. So the second electron will have minus half, right? So if you look at the values of all the 4 quantum numbers of these 2 electron, even it present in the same suborbital, the value of n is same, the value of L is same, the value of M is also same. But coming to the spin quantum numbers, these values differ because of the direction of spin of the electrons. So from this we come to know that no 2 electrons in an atom can have the same set of all the 4 quantum numbers. Definitely at least the value of one quantum number will differ from each other. Pauli's exclusion principle also stated that only 2 electrons may exist in the same suborbital, whether it is an s orbital or p orbital or d orbital. Only 2 electrons may exist. How many p orbitals are there? 3, right? P orbital in the x direction, p orbital in the y direction, and p orbital in the z direction, right? So 2 electrons will be present in the px orbital, 2 electrons in the py orbital, and 2 electrons will be there in the pz orbitals. On the whole, how many electrons will be there in p orbitals? P orbitals can accommodate 6 electrons. Coming to d orbitals, how many d orbitals are there? There are 5 d orbitals, right? What are they? dxy, dyz, dzx, dx square minus y square, and dz square, right? So each d orbitals can accommodate how many electrons? Only 2 electrons. So on the whole, how many electrons will be there in the d orbitals? There are 5 sub-d orbitals. So 5 into 2, 10 electrons will be there in the d orbitals. If the question is how many maximum number of electrons present in an orbital or suborbital, then the answer is 2 electrons. So Pauli's exclusion principle stated that only 2 electrons may exist in the same suborbital, whether it is px orbital, py orbital, or pz orbital, or s orbital, or any one of the d orbitals. And these electrons which present in the same suborbital have opposite spin, right? So one in the clockwise direction if it spin in the downward direction, and another one will be in the anti-clockwise direction if it spins in the spin up direction. If the question is how many maximum number of electrons in a shell with respect to the principal quantum number n, then the formula is 2n square. If you take this K shell, what is the value of n? N equal to 1. If you apply this value of n in this formula 2n square, then 1 into 1 square is 1, 2 into 1, 2. So what is the maximum number of electron in the K shell? Is 2. What is the value of n? N equal to 2 for L shell. If you substitute the value of n equal to 2 in this expression 2n square, then 2 into 2, 4, 4 into 2, 8. So the total number of electrons, that is the maximum number of electron present in the L shell is 8, right? 2 in the s orbital in the L shell and 2 in the px orbital, 2 in the py orbital and 2 in the pz orbital. On the whole, how many electrons will be there? 8 electrons. So if the question is what is the maximum number of electron exist in a suborbital or orbital, means the answer is 2 electrons. If the question is what is the maximum number of electron in a shell with respect to the principal quantum number n, then the value is 2n square. Hope you could understand these two concepts clearly. Now let's see the third rule, that is the Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity deals with the filling of electrons in a suborbital in the same shell. For example, let us consider the degenerate p suborbital in the same shell, that is the L shell. What is the meaning of degenerate p orbital? Degenerate means in the absence of electric or magnetic field, the three orbitals of a particular energy level have the same energy. Pairing up of electrons takes place only when there is no empty orbital. If an empty orbital is available, pairing up of electrons does not take place. To understand this concept, imagine if you and your friend are entering a room where only 2 chairs are available. You sit individually in each chair, right? After some time, if one of your friend is entering that room, then one of you will share your seat, right? Your chair. If another friend is entering the room after some time, then the other person will share your chair with him, right? Likewise, the pairing up of electrons takes place only when there is no empty orbital. While filling orbitals of equal energy, pairing of electrons is avoided as long as it is possible because they experience a greater repulsion. We know that the maximum number of electrons that can accommodate in p orbital is equal to 6 electrons, right? In case only if 3 electrons are available for p orbitals, then each electron will occupy each suborbitals individually. Pairing won't take place when there is an empty orbital. Moreover, the electrons in the singly occupied orbital should have a parallel spin, which means if the electron in the px orbital spins upward, then the electrons in the py and pz also spins upward, because parallel spins corresponds to a state of low energy. If there are 4 electrons are available for a degenerate p orbitals, the first 3 electrons occupies each of the p suborbital, and then the 4th electron will pair up with the px orbital. The application of these 3 rules has been illustrated in electronic configuration, which we are going to see in the next session. Students, I hope now you are very clear with all the 3 rules for filling of orbitals in an atom. Now let's recall all the topics that we have discussed in this session. In this session, we have discussed the rules for filling of orbitals in an atom, that is Aufbau principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. Hope this session was very useful to you. See you soon in the next session. Have a nice day. Thank you.